Dear student, in this lecture we will learn about R2 to R ladder D by A converter. In our previous lecture we had already discussed about binary weighted register, digital to analog converter, and we have seen in that lecture that the R2 to R ladder D by A network is most popular in comparative to weighted register D by A converter due to its accuracy and ease of manufacture. So let's start with the basic introduction of R2 to R ladder D by A converter. Student, this converter is basically used to convert digital information into an analog output. It is suitable for IC fabrication because it has only two resistors R and 2R. It is most popular converter in comparison with binary weighted ladder D by A converter due to its accuracy and ease of manufacture. So here we will consider the 4-bit R2 to R ladder type D by A converter. In this figure, this is the basic R2 4-bit R2 to R ladder type D by A converter. Here these are the resistance R and these are the 2R resistors, and here this is the terminated resistor 2R. So here these are the binary digital input bits B1, B2, B3 and B4. If we will consider here, this B1 is equal to 1 and these B2, B3 and B4 are 0, 0, 0. So this B1 will becomes MSB. This is the most significant bit and this is the least significant bit. So here this figure shows the 4-bit binary inputs B1, B2, B3, B4 and the output voltage V0 and one terminating resistor 2R. So in this circuit the output voltage is a weighted sum of digital inputs. So here we will calculate the output voltage V0. So now draw the equivalent circuit of 4-bit R2 to R ladder type D by A converter. So this is the equivalent circuit and here this is the reference voltage and this is at the most significant bit, that is B1 equal to 1, and these are the B2, B3, B4, these are 0, 0, 0, and let's assume that these will be grounded. So we will ground it here in these terms B1, B2, B3 and B4. So here in figure this last we will see here, this is the last portion of bit B4 and these two resistance 2R and 2R, these are connected in parallel. So if we will find out the equivalent circuit of this last bit portion, then this will becomes equal to R. So why this will becomes to R? So this is the equivalent resistance equal to, because these are connected in parallel, so this equal to 2R parallel to 2R. So now 2R into 2R upon 2R plus 2R, and this will becomes R. Now again we will draw the equivalent circuit of that figure B, and this is the here we will consider the resistance R, because we already find out this resistance in figure B. This is R. So now we can redraw this circuitry, and this circuitry will become like this. In this shows in figure C. Here the resistance R at this because we will remove this B4 term here, and this is the equivalent resistance, that will be R, and this is remaining bit is B3 here, and so now we will see here this is R and this is R. These are connected in series and these are connected to into the 2R in parallel combination. So now again find out the equivalent circuit in this portion in last B3 bit. So here again this R equivalent resistance will be equal to R. So here again we will draw the equivalent circuit of that stage of figure C. So now we will draw this here. R, again this is connected in series, and this is again these R plus R are connected in parallel to 2R. So again we will find out the equivalent resistance, that will becomes R. So here again we will draw the circuitry of figure C, D. So this is figure E. This is equivalent circuit of the third stage. So again this is now become the circuit is R, R, and this is 2R. Again this is these resistance are in series, and these are connected to into the parallel of 2R. So again by applying the Thevenin theorem, the output voltage becomes V naught is equal to VR into 2R upon 2R plus 2R equal to VR by 2. So here this is the how to calculate this one. So we can draw the equivalent circuit, Thevenin equivalent circuit of the circuit, and here this when we will find out the output voltage, that is equal to V naught, and this is equal to VR into the resistance 2R upon the total resistance is R plus 2R. So this will be like this, V naught equal to VR by 2. Now when we consider here the B1, B2, B3 and B4, these digital bits are equal to 1 0 0 0, then the output is VR by 2. We have already find out this output voltage, that is VR by 2. So now we will consider here the B1, B2, B3 and B4. These are equal to 0 1 0 0, then the output will becomes VR by 4. We will find out this output voltage like this. So the output will becomes VR by 4. Now this B1, B2, B3, B4, if these digital input bits are equal to 0 0 1 0, the output is VR by 8. And now we will consider here B1, B2, B3, B4, these bits are equal to 0 0 0 1, the output will become VR by 16. So since the resistive ladder is a linear network, here the principle of superposition we will apply here, and we will find out the total output voltage of the circuitry. So if this circuit is considered here like n bit D by a converter, then the output voltage will be V naught equal to VR by 2 raised to power 1 plus VR by 2 raised to power 2 plus VR by 2 raised to power 3 up to VR by 2 raised to power n. Here n is the total number of bits. So now if we consider this circuitry using operational amplifier, then the circuit will becomes like this. Here this is the operational amplifier, and this is the feedback resistance, this is the another one resistance, and this op-amp is work as summing amplifier. So these are the various inputs of the summing amplifier, R, 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 and these are the 2R, 2R, 2R resistances here. This is again the terminating resistor 2R. So here finally if you find out the output voltage of this circuitry, so this circuit the output voltage will become equal to, because in case of operational amplifier the output will becomes equal to gain into input voltage. If the circuitry is work in inverting mode, then the gain will be minus Rf upon R1, and if the circuitry will becomes in non-inverting mode, then the output then the gain will be 1 plus Rf by R1. So here this is the Rf upon R1, minus Rf upon R1 represents the gain, and because this is operational amplifier is work as in summing mode, as a summing amplifier. So here these are the sum of input bits. So this is the minus VR into the gain Rf upon R1 into b1 upon 2 raised to power 1 plus b2 upon 2 raised to power 2 plus b3 upon 2 raised to power 3 plus b4 upon 2 raised to power 4 or up to n bits. So here these are the this is the 4-bit ladder type D/A converter using operational amplifier, and this R2 to R ladder converter D/A converter having so many advantages, like it is scalable to any desired number of bits. The output impedances are regardless of number of bits. The binary word length can be increased by adding required number of R2 to R sections. Thank you for watching.